All right, let's take a look. First, look at our two most popular reducing agents. So here, what we're going to do is we're going to take some kind of carbonyl, and then we're going to reduce it into some kind of alcohol, right? So this H in bracket generally refers to reduction. You can think about it as adding an H minus. So we can do this with a number of reagents. The two most popular are sodium borohydride and lithium aluminum hydride. So if we take a ketone such as acetone and we add some sodium borohydride, usually in some kind of polar protic solvent, usually an alcoholic solvent like ethanol. And then in the second step, we just add some acid to reprotonate our alcohol. We will get an alcohol. We can also use lithium aluminum hydride. Although generally when you can use sodium borohydride, when that's going to do a good enough job, you want to use that, as the lithium aluminum hydride is much more reactive and you can start fires with it. But sometimes it is necessary. The role of the borohydride and the aluminum hydride are basically just to act as a source of H minus. So here's the borohydride picture. And so in this case, the boron has the formal negative charge, but hydrogen is actually more electronegative than boron. So all of these hydrogens are actually partially negatively charged. Even though boron's got the negative, it's really the hydrogens that have the electron density. And so this is equivalent to approximately an H minus. The reason that we don't just use H minus is because H minus is a very good base, but not so good of a nucleophile. When we use sodium borohydride, essentially what we're getting is an H minus, but more nucleophilic. And the reason for that has to do with polarizability, but we won't go into it as much. Let's go take a look at the mechanism of this. So another thing before we take a look at the mechanism is we want to think about our carbonyls, right? I just gave you a hint that the hydride is nucleophilic. That means our carbonyl is going to be the electrophilic component. And if we think about it, that makes sense. We have a net dipole right here where the carbon is partially positive and thus electrophilic. So what's going to happen is about what you kind of expect to happen. We have our electrophile. We have our nucleophile. And the way we're going to draw this is the bond from the BH is going to attack the carbon in the carbonyl, and then the pi bond from the carbon-oxygen bond is going to break and become a lone pair on the oxygen. Note that although we're drawing this coming from the bond, the electrons are going to stay with the hydrogen, and then the boron is just going to lose some electrons here. So then our intermediate here is this O minus, and now we've attached our hydrogen onto it. And then of course here we just have BH3 left over. After that, the second step is to just add some acid, and that's just to reprotonate our alkoxide. And then we get our alcohol. I've omitted the hydrogen here. This is going to be a racemic reaction. So you're not going to get any, R or S preferences. You're going to get a mixture of both. These reductants will only reduce carbonyls, so they won't reduce alkenes. So if you have a molecule that has both a carbonyl and an alkene, you can use either one of these, the lithium aluminum hydride or the sodium borohydride. They'll both do a good job of reducing this. Without touching the alkene. When you'd want to use lithium aluminum hydride over sodium borohydride is when you have carboxylic acids or esters. So lithium aluminum hydride can reduce esters and carboxylic acids, while the sodium borohydride cannot. So when you need to do a more powerful reduction, you can use the lithium aluminum hydride. Otherwise, you're better off using the sodium borohydride for safety reasons. So for example, if you have a carboxylic acid, you can reduce that through the use of some lithium aluminum hydride, and then just do an aqueous workup to reprotonate your alcohol. And of course, this works on esters as well. But again, only lithium aluminum hydride can do this. Sodium borohydride cannot. The mechanism is pretty much the same for the lithium and the borohydride. Let's go ahead and take a look at this, but this time with an ester, right? So we've got an ester now, so the second part of the mechanism will be slightly different because we didn't have that previously. But the first part is the same. Right, we're going to use our hydride delivery reagent to take this hydride, this H-, attack our carbonyl, break that carbon-oxygen pi bond. To get this component right here. And then what happens here is that this negative charge from this oxygen bounces back to become a pi bond, but this time kicks out this alkoxide. To get at first an aldehyde, however, we can't stop here. We need to continue our reaction, and we will actually reduce further. So again, we're just going to add another H here. And then finally, we just reprotonate to form our alcohol. Carboxylic acids. This reaction works for carboxylic acids as well. We'll take a look at the mechanism later on. It's a little bit more complex, but not too bad either.